academician of Russian Academy of Science, Alexei Lvovich Semenov. His report is yeah, thank you. Finiteness and complexity in the time of AI.
So I have an honor and a pleasure to work with Andrei Kolmogorov, Professor Kolmogorov, for last period of his life in our department of mathematical logic and theory of algorithms. And so many ideas which I grasped from him in these years will be explained in my presentation today. Yeah, there's a kind of subtitle about Kolmogorov and the digital. Some of reflections of what we've discussed with Andrei Nikolaevich was that the perspective is changing. Before that time, or before now, finite was considered as approximation to infinite. And in his vision, infinite became, or infinity became approximation to finite. And finite becoming more important for our world and at least for our science of mathematics today. And if you consider the whole history of mathematics in 20th century, we'll see some coincidence. From one hand side, the century started with Hilbert's attempts to build foundations for mathematics. And other people joined him, but Hilbert definitely is #1 figure in mathematics of that time. Even in the 19th century, Italians and Germans also worked in this direction. At the same time, 20th century is a remarkable century, is a unique century perhaps in the history of humanity, because it was that time when digital era started. Again, something was happening in 19th century, like transmission of signal or wired telegraph or photography. But the more things happened, of course, in the 20th century. And so there is these two things, the attention to foundation of mathematics and the emergence of digital era. But I don't think it was really a coincidence, because the foundations of mathematics became as well the foundations of the digital technologies. It's an evident circumstance, and that's the reason also for this interesting conference we are present today. Just to mention interest of Kolmogorov to these foundations, in years of 20th and 30th of last century, he published, as you perhaps heard, 2 remarkable papers. At this moment, his interest to the foundations of mathematics were concentrated around what's called Intuitionism. It's an attempt to have some kind of constructive, in general sense, view on mathematics. I will not go into details here just to save some time. Also, it's an important text of him in his letter to his teacher, the great academician, as it was many times said today, Professor Nikolai Luzin. In October 1945, Kolmogorov wrote to Luzin about his, Kolmogorov, emerging interest to foundation of mathematics in the scope of what is called theory of algorithms today, of works of Turing and Church. It was, purely scientific, mathematical reason, but also he had some interest, as usually happened with Kolmogorov, in practical things. So just in the time of digital computers emerging, he bought for his own money 10 Felix arithmometers. I don't know if you've ever seen this device, but it's kind of natural size, like a personal computer, but with the handle you can turn, and then you can calculate and make even long division, about I think 10 digits with this device. One more example of his interest is his report to the Moscow Mathematical Society in 1951, again about digital schemata, about the digital devices, algebra of 2-bit functions, etc. Kind of resume for his activities of this year was in his report to the International Congress of Mathematicians in 1970. Of course, you know that this is the major event in mathematical life over the last century. It's an International Congress of Mathematicians. The second Congress, I think it was the second Congress, it was this one when Hilbert proposed his list of 23 problems, including problems from the foundations. So the first chapter in this talk of Andrei Kolmogorov was called on the increasing role of finite mathematics. And he was saying that the mathematics is developing successfully as primarily the science of the infinite. Until recently, mathematical natural science was dominated by modeling of real phenomena using mathematical models based on the mathematics of infinite and continuous. And then he refers, I will not read because you can read it faster on the screen, he reference to the God, that this was given to mathematicians by the God. It's interesting that it was written in and pronounced in 1970, when the reference to the God was not really usual and even permitted in our country. But he says that now artificial intelligence is coming, and we should change our perspective. We need to concentrate more on finite. Again, about the building of computer science, there were several reports of Kolmogorov, and to mention one of them was the definition of algorithm. You've heard, of course, about the definitions of algorithms, like Turing machines or whatever. But essentially, we consider different definitions, like the definition of what can be called computable function. In an old terminology, it's called partial recursive function. Perhaps you can find it in some old text. But today we understand it means a general notion of computability. A function not, of course, with the whole range of natural numbers or whole words in alphabet, with a partial function. But anyway, we speak about computability. But Kolmogorov tried to go deeper and give a definition, not of computable function, which was known at this moment, but definition of algorithm. And that was, I think, interesting attempt. So his idea was that something which he called algorithm in general sense can emulate, simulate, model any specific algorithm in any specific algorithmic language if the complexity of one step is limited. So that was an idea. It was called later Kolmogorov-Uspensky machines or Kolmogorov-Uspensky algorithms, because it was finalized and published with his student Vladimir Uspensky, whom also some of you know pretty well. So what's happening in this moment? It was inventing of digital computers, like physical devices, with some vacuum bulbs, or before this even the relays, electromechanical relays. But mathematicians also played a crucial role in this. You can consider more seriously what was happening in UK with the involvement of Alan Turing in this. Actually, he was a key figure in the original, even technical design of first computers, not to mention even this, his work for military deciphering before, during World War II. But after World War II, he was very much involved in the design of first British computers, which were happening simultaneously with what's happening in the United States. Of course, we better know about events in the United States and in Britain, but really it was going in parallel and in contact. Actually, Turing spent some part of his 30s in Princeton, New Jersey, and communicating with such people, the Church and Post and others. In Russia, it was happening a little bit later. So there is a standard anecdote discussing here about Bashir Rameyev. You can see his photograph here. He never got his master degree because of his father was persecuted during the Stalin time, which was pretty usual for a different part of the population here. But he said that he heard about the computers, digital devices in the United States to be developed. And he decided to develop the same thing himself. And in 1946, 48, he did this in some institution in Moscow. Another great name is, of course, the name of academician Lebedev, who is here. And of course, you can recognize Alan Turing and John von Neumann. So it was really a lot of interest from Andrei Kolmogorov in this time, and he was not so active in public lectures, but in this time his lectures on, for example, automata and life collected, several hundred people in the places in Moscow, and essentially it was about what was called cybernetics at that time, and computing and artificial intelligence. And one example, well-known example, is he, in the beginning of 60s, he started a seminar on complexity and proposed that the first problem to solve is to prove that you cannot multiply multi-digit numbers faster than in quadratic complexity. And a young student, Anatoly Karatsuba, in a couple of weeks proposed to him the algorithm which makes it faster. Actually, later it was kind of indicated that something to this extent was made by Gauss, but not essentially. There is a nice paper of Alexander Shein in Math Prosvещение on this. And one more thing is here, proposed to his student, PhD student, Jan Martinovich Barsdin, a problem of how can you pack networks into 3D space. So again, he was thinking that computers is something which can work physically. And his algorithm of Kolmogorov-Uspensky machines, they are graphs of very sophisticated structure, and how you can implement this in the hardware, what we call today in silicon. Just one mention, at the same time he was working in classical mathematics, one of the Hilbert's problem, and with his student, another student of him, Arnold, he proposed what is called today, what is mentioned here, reference today as Kolmogorov-Arnold networks. And first publication, I believe, was a Czech researcher, Vera Kurkova. Today we've heard about some big numbers from time to time, and big complexities of these problems. It's essential, of course, for artificial intelligence. An attempt to classify numbers by their size was again in Kolmogorov lecture of 61. He was saying that there are small numbers which you can sort everything. You have 6 objects you can place on the table, you can order this on this way, etc. And other sizes like medium numbers, large numbers, and extra large. And he said that for extra large numbers, we don't need them at all. He said also that perhaps my classification of the size of numbers depends on our human abilities, and we will have computers. The classification of different, scales for numbers will be different. An important milestone in his work was his visit of India. He traveled to India via ship, via boat, actually, in 1962, and this is his photography from the Indian Institute of Statistics. I think it's the same Institute of Statistics. You can see his photograph here, the Kolmogorov with bare feet and all these Indians around him in the Indian Institute of Statistics in 1962. When he published his paper on tables of random numbers, the paper which started the Kolmogorov complexity story. It's interesting again that this paper is about only finite objects. Kolmogorov complexity today is a field of infinity, mostly, like Nikolai Vereshchagin work and Alexander Shen and Duran and Vitani and everybody. But his original interest was, he said that theory of probability, he proposed the mathematical foundation for the theory of probability in 30s, the theory of measure. And he said that it's unexplainable that this infinite consideration has any relevance to our life, because we work and we deal with the finite objects only. And that his paper, when he started to work just with finite things, what means that the finite sequence is random in this or that way, which for infinity is not interesting, because it's not random, it's just, short sequence, which not random at all. But his thinking was we should define what means for it to be random to that extent. So we need some tests were proposed by Church, etc., but I will not go into details here, but I just indicate he's interested from the beginning to this. And he was very much unsatisfied, saying that he gets some upper and lower bound for number of tests which can find is it random or not random to that extent. He tried, but these upper and lower bounds have a big discrepancy in them. And actually, my student, late Andrei Muchnik, really a genius, and with myself, proposed a solution after 40 years, in fact, for this problem. And our different discrepancy was between 900 and 1500, not even in multiplication in power. So that was our feeling at that moment. And the story about random tables of random numbers developed to something which was mentioned today in the talk of Ivan. It's a Kolmogorov complexity. And at the same time, he started experiments. He proposed to his workers from his laboratory on statistics to continue long texts in Russian language, like text from a novel of War and Peace. What will be the next word? It was exactly a kind of experiment with human GPT. But he was mentioning Shannon, Claude Shannon. He expected Shannon, who was an engineer, very much. And he said that Shannon tried to do something like this in English language. But for Kolmogorov, he measured abilities of different of his friends and students with the guessing what will be the next. Eventually, he wrote a paper, three approaches to the definition of concept of quantity of information, and while publishing, he was mentioned by somebody, I don't remember, could be even a winner, Nobel winner, that American engineer Ray Solomonov invented something very similar, more or less the same, but again, it was his, Kolmogorov was kind of logarithm that was developed by Solomonov. And an interesting thing, I believe that some of you had a lecture on Kolmogorov complexity, or even presented the concept of Kolmogorov complexity to some students or your friends, etc. And usually we apologize, saying that yes, Kolmogorov complexity is a nice thing, but you know, there is this additive constant that you have an optimal way to describe everything. But optimal in the sense that another way of description, another mode of description has a difference. Another mode can do any constant better on some element that the optimal algorithm. So what does it mean optimal? So at the same time, Kolmogorov wrote in this famous paper of 3 approaches, then actually the optimal way is not so bad. It's only on some tenth of bits worse than another one. It sounds a little bit strange, and also the same observation was made by Leonid Levin. I will not go into details in his thing, but what does it mean that the discrepancy, the difference will be just in tenths of bits or hundreds of bits? Because if you have some big object, like in big data, and put it inside an algorithm, which is happening essentially in large language models, then you have again a very big discrepancy. It could be thousands or millions, etc. And it's strange why we consider unnatural to install to hardware some big piece of information into a specific algorithm. So I propose now a change in Kolmogorov definition. So just very simple. Let's assume that we add to standard Kolmogorov definition of the minimal size of the description just the length of the description mode of the algorithm which describes it. So L means length here. So in this case, we can again prove Kolmogorov optimality algorithm, and we can have some logarithm addition to this. It's more or less clear if you understand what it's about. But this is not about computable functions, about algorithms. And if we think now how big this difference between optimal Kolmogorov description of everything in the universe and another which can be better, that the difference will be the size of universal algorithm and this logarithm. Logarithm of size of something, it's just nothing. It's just definitely less than 100. And length of universal machine also can be pretty small, because you can describe universal machine as something very small, like 6-state Turing machine, or the life game or something like this. So in fact, the paradox which was explained on the previous screen can be solved just by this modification of classical Kolmogorov definition. So that's first mathematical sense, or round mathematical sense, I was going to describe there. And another story about complexity is about NP-complete problems. And perhaps we can reconsider the situation about them. As you know, some of the SAT solvers really work rather effectively. And perhaps we should build a mathematical theory about this situation. Also, at some moment, Turing proposed the idea of oracle. Oracle is an essentially infinite set, which can be used helping us to solve this or that algorithmic problem. And classically, of course, we consider oracle as an not decidable set, or not even enumerable set, but something very, very sophisticated. But if we consider again the finite situation, we can use finite oracle, but very big one, like happens with training neural networks. And so the question here is how to formulate adequate quantitative computational model. What should be definitions and theorems? If we can drift from the classical, say, Turing definition of Turing machine to this new definition when we can use finite but very big oracles. How we can define everything for this theory of complexity. Size of the oracle, size of the trained network, size of the prompt, and size of the output. So it is like here. We can, for example, say that today we have a limit of size of the universe. It's 10 in, say, 100 or 73 or whatever you like. But then you need a new complexity theory when you have this scale of biggest sizes, smaller sizes, etc. And what will be the complexity here now? For example, we discussed with Sergey that they were talking about polynomial complexity in your situation. At the same time, Sergey said, for example, there is a polynomials for work with algebraic numbers, but these polynomials have some huge, power, and it's not realistic. So there is some sense in considering new theory of complexity. And then I would like also to say that the idea that some numbers are too big to consider it as finite belongs, for example, to Paul Bernays, a co-author of Hilbert and Bernays' book on the foundations. He said, for example, that why we think that 67 in the power of 257 in the power of 7 to 9 really exist. Nobody knows. But actually, of course, this exists because it's written here. But if other people also were interested about this situation of existence of some big numbers, but actually, if we consider not the size of the decimal notation of the number, y decimal, y notation, etc., but consider any way to explain, to describe the number with any kind of algorithm, then we can see that some objects in the universe have no description there. And that's more doubtful, do these numbers exist? If, of course, there is no algorithm which fits in the universe, and there is no prompt to this algorithm which gives you the number. In this case, really, the number perhaps does not exist. And that's one no. And coming back to Hilbert, his idea was to produce a foundation for the, I will need perhaps, sorry, 5 minutes more, for the mathematics. You know, it was ruined by Gödel, who said that it's impossible to prove completeness of mathematics. In mathematics, you will have very short sentences which are not proved. At the same time, it's an interesting question about consistency. Could it happen that there are some contradictions in mathematics, but the contradictions will have size greater than the universe? So it's something which is not solved. Different people were trying to do something in this direction, but very little was done. So essentially the problem is again, perhaps mathematics, real mathematics which work is really consistent. There is no contradiction in this forever. Never no human will come to a contradiction just because contradiction is too big. It's something we should think about. Sazonov is mentioned here, and some other people, like there is something about the student of Alexei Belov, who is present here, that some mathematics is very hard to understand, if not in a visual form, like with existence of aperiodic sequences in some outer billiards. Yes, not mentioned here. Yes, one thing about Post, Post proposed something which is called tag systems. You have a word, a finite sequence. You take something from the beginning, say 3 symbols, and cross it out, but using the first symbol to put something to the end. One of the examples of this system is connected with Collat's conjecture and Collat's system. It is written here with, yes, the fourth system corresponds to Collat's conjecture. And nobody knows are there infinite aperiodic sequences here or not. Post himself proposed this last one with 2 letters alphabet, 3 letters from the beginning you cut off, and then put 00 or 1100 to the end. There is a young mathematician from Moscow University. It looks, his name is Kurilenko, Igor Kurilenko, who published a proof for this. It's interesting, he published this in Wolfram's magazine, Open Access. Yes. I asked different people, try to understand the proof of Kurilenko, and I did not succeed. Nobody can find a proof for this. So his idea is, in post system, there are some infinite non-periodic sequences, and this is an example. And if you just put it into the computer will give you really more and more digits. So it's a solution of post system, which Wolfram did not solve. But we don't have exact proof. At least I cannot find it in the Kurilenko proof. And the last thing I would like to mention is that there is another famous problem, of course more famous than posts, is Burnside problem. You know that Novikov and Adyan gave a solution to this, but there are cases of small exponents that consider a group with 2 generators, with every element of group in the 5th power equals to 1. Can it be infinite? It's known that among all finite groups, there is a maximal group, and it has 5 in power 36 elements. It's a big number, but not so big. There is actually a paper from people from Krasnoyarsk who kind of visualized this big finite group. There is no bigger finite group, but perhaps there is an infinite group. And perhaps there is a way how to use artificial intelligence in guessing sequences, what will be the next, in guessing, in kind of game playing with this to be infinite Burnside group, to find the different objects, different elements in the amount more than 5 in 36 power. And the last thing is that actually a difference can be done even in education, on the level of school education. We're working with these small objects which are visual in 1 page, and think it's better introduction in mathematics than natural numbers, because natural numbers are very non-intuitive, non-clearly written. If you have the distance 286, you cannot differentiate for a difference for a distance 287. And for a small one, it's not evident things. It's a very sophisticated symbolic manipulation to go from number to its digital format. We are now trying to work on a new agenda, new proposals for school, and for the high school it's working with Alexander Gasnikov on the project how you can train, teach elder in specialized mathematical schools to work on mathematics immediately coming to artificial intelligence problems, either discrete and symbolic and infinite and continuous. So that's the end of the story here. Thank you.
Okay. Thank you for great report. Maybe you have a question or remarks? No questions. Okay, thank you. You can ask academician Alexei Lvovich on the break if arise some questions. Okay, we go next.
Maybe a short remark. You mentioned Durand, beyond Durand. I want to say that he is president of French Mathematical Society right now.
Yes, yes, and one of the research with Sheny and Vereshchagin and Andrei Muchnik happened because our connection with Durand and some of my visits friends. Yes.
Yeah.
Yeah.
Thank you, academician Alexei Lvovich. Okay, we go next. Next speaker is